Hey guys, F-Train here. First astronomy lesson of the new era of home instruction. Anyway, I hope you guys are doing okay. Hope everybody's well, and hope you guys are not too bored. And I'm gonna try to give you this lesson. Not really supposed to give you work until like Monday, but I figured some of you guys might want to get started on this. So there's no rush to get this done. But anyway, my goal is in these lessons to try to make them like 15 minutes ish. So I'm going to kind of keep track of the time. It's like 3:05, so try to be done by 3:20. So that way, it's not a lot, very time consuming. So what you might want to do is pause the video if I'm going too fast. Now you'll notice there's a do now here. Why do massive stars live shorter lives? And if star A's mass is double that of star B, how many times longer will star B live? So why don't you go ahead and pause the video while you answer that, okay? All right, so now in terms of our last lesson, which was seems like forever ago, but maybe it was about a week ago, we learned that the star's lifetime is 1 divided by the mass to the 2.5th power, where T is the lifetime in solar lifetimes, M is the mass of the star in solar masses. So let's just, first of all, we know that the greater the mass is, the shorter the lifetime, right? Obviously, because it's an inverse relationship. And then let's say star B's mass is 1 solar mass, then its lifetime would be 1 divided by 1.2, 1 to the 2.5, which is 1 solar lifetime, okay? But then let's say star A's mass is double that, then you would do 1 divided by 2 to the 2.5, which is 0.177. That should be a point. That's like a European way of doing it or something like that. So anyway, 0.177 solar lifetimes. Which turns out to be about 177 million years. All right, and we get to see that again. All right, so explain this picture. And again, if you want to pause for a second, this should look familiar to you, but I'll give you a second to think about it. That is the Orion Nebula. And as you can see, if you look at this little glowing spot here, okay, we're going to talk about what that is. It's not a star. There's lots of stars there. These, some of the big stars, Betelgeuse, etc. But this is not a star, and it's actually a cloud. Okay. So before stars fall into the main sequence, they start off more luminous and at a lower temperature, which describes what they call a pre-stage zero sequence. And so therefore stars must start somewhere. So any questions? Oh, I thought I heard somebody say, where are stars born? Yes, that is our aim for today. Where are stars born? Okay. Stars are born in what we call the interstellar medium. Now, if you look at this picture here, this is called the Crab Nebula, all right? This is basically a remnant of a supernova, okay? And I think we might have learned about this in the past. But anyway, what is a nebula? Well, a nebula is a low density cloud of gas and dust that sometimes absorbs light and sometimes emits light. Nebula have densities even as low as 1 atom per centimeter cube, which if you think about it, that's like, a billion million times less dense than air. Not very dense, okay? But this is the birthplace of stars, okay? There are basically 3 types of nebula, okay? There are going to be emission nebula, which are also known as singly ionized hydrogen nebula. Basically, the way an emission nebula works is you have this cloud of gas, and you have ultraviolet light from a very hot star. We know white dwarfs are extremely hot, And so what happens is that the ultraviolet light will basically excite the atoms, and we learned about how when the energy level of the electrons increases, they get excited, they drop back down, they emit light. So that's how they're going to emit light, because they have to get excited by something near it, like within that cloud, like a very hot star, like a white dwarf. Okay. This picture here is called is called the Trifid Nebula, and it's an example of an emission nebula. Okay. There's another emission nebula known as the Carina Nebula. See, some of these pictures are very beautiful. Now, what determines the color of the nebula? Well, you might have learned this in the past, but hopefully most of you guys have thought about why is the sky blue. Okay, and if you look at the sky when you're on the pictures taken from the moon, the sky is black. Okay, on Mars the sky is red. So why is the sky blue? Well, it turns out that as the sun's light comes in, and you can see the sun's light coming in, all the different colors, when it hits our atmosphere, basically what's going to happen is the longer wavelengths will pass through, but the shorter wavelengths like blue and violet are going to get scattered. What that means is they basically just get reflected, or they actually get absorbed and re-emitted in all different random directions. So that's why if you look up in the sky over there, even though the sun's over there, you can still see brightness because the sun's light is being scattered from those molecules in that direction. Second type of nebula called a reflection nebula. So essentially this is an example of that. Reflection nebula scatters starlight from blue light basically gets scattered more than red, and so and since there's very small particles in the atmosphere, nitrogen is what scatters the light molecules, or the light photons, but in a reflection nebula it's usually like little dust particles and things like that. Okay. And these little dust particles, are made not of stuff like under your bed, but more like molecules and ice and things like that. Example of a reflection nebula. This is called Messier 78. Okay. Third type of nebula is called a dark nebula. Basically, these are dense clouds of gas that essentially just obscure the light from distant stars. So you can see here, this picture is called the Horsehead Nebula. This is one of the most famous pictures of a nebula that you'll see. It actually kind of looks like a horse, as you can see. This is a close-up of that picture. This is called the Elephant's Trunk Nebula. I don't know if you can kind of see the ears of the elephant, and then that's his trunk. This is called Barnard 86, the Black Cloud Nebula. Okay. This is a nebula that was kind of discovered recently called the F Nebula. It actually looks very similar to the letter F. Now, why are sunsets red? Okay. Well, the answer is kind of similar to why the sky is blue, okay, but not. So basically, during a sunset, what happens is that the sun's light is kind of passing through the edge of the atmosphere because, the sun is very low, so it has to go through a lot of the atmosphere. And what happens is that the longer wavelengths, like red, pass through, whereas the shorter wavelengths get scattered, okay? And so by the time the sun's light gets to us, okay, by the time the sun's light gets to us, all that you see, all that's left is the red light. The rest of the light has gotten scattered, okay? So describe the effect that a bunch of dust and gas would have on the apparent magnitude of a distant star. Well, it's going to decrease the magnitude. Okay, so interstellar dust makes distant stars look fainter. Okay, and you can get up to about a 1 magnitude decrease in brightness per 1,000 parsecs. Now, 1,000 parsecs is a very, very long distance. So even though there's not a lot of there's not a lot of molecules per, let's say, cubic centimeter. You know, if you add them up, there's actually a lot. Okay, so the red light glows through, but blue light is scattered. Now, if you look at, here's a picture. If you look on the upper left, here's a star. White light coming through, passes through a molecular cloud. The shorter wavelengths get scattered, and the red photons make it through to your telescope. Okay, this is a picture of the Black Cloud Nebula. You'll notice that if you look at this picture taken in a visual wavelength, see it says visual down there. You don't really see much of anything. But if you were to look at a picture taken in infrared, you can actually see the stars, and that's because infrared light will go through the gas and the dust and everything more easily even than red. It's longer wavelength. Okay. Hot O stars are too hot to have ionized calcium absorption lines from their surfaces. Okay, so we would rather expect to see, if you look at really hot stars, calcium's way down here. We would expect to see, helium, singly ionized helium lines. Okay. However, we often do see calcium lines observed even from hot O stars. How could this happen? Well, the answer would basically be that there are it shows us that there are interstellar gases in front of the star that are absorbing those calcium lines. Okay. How can lines come in multiples? Well, we learned about the Doppler shift. So you can imagine if part of the cloud is moving, let's say the cloud is turning, part of the cloud might be, moving towards us, or a different cloud moving towards us, and one cloud moving away from us. So you could get, shifting of those lines. You'll notice, so why are interstellar absorption lines narrow and sharp? We talked about the fact that if you have a thick atmosphere, the absorption lines get broadened. They call that pressure broadening. If there's because there's more collisions and things like that. Because these gas clouds are very, very low density and low temperature, the absorption lines are very narrow. Okay, because there's very few collisions. There's also something called forbidden lines. Okay, forbidden lines are basically transitions that we never really see in laboratories on Earth. For example, we see strong green lines at 495 nanometers and 500.7 nanometers. We've never seen these kinds of lines in laboratories on Earth. And these are produced by doubly ionized oxygen. And what happens is because there's such low amount of disturbance in interstellar space, the transitions, rather than the electrons dropping down immediately from one level to the next, they can actually stay in these metastable states for up to an hour. Due to the very low density, and there's no other collisions taking place. And so when they drop down to the next level, they'll emit these lines that we never see on Earth. If the density was not very low, they would get re-excited before they release these forbidden lines. Okay, here's some examples of those forbidden lines. Okay, again, we talked about the constellation Orion. Here's the Orion Nebula. And so I believe the remainder of the pictures here I'm going to show you are just some examples of really cool looking nebulae, and I hopefully will have met my goal of not keeping you more than about 15 or 20 minutes. Here's called the Eskimo Nebula. This is the Hourglass Nebula, the Ring Nebula. I showed you before the F Nebula, the Veil Nebula, the Eagle Nebula, Pillars of Creation. This is actually one of the most famous pictures that was taken by, I believe, the Hubble. Okay. The Eye of Sauron Nebula. It's kind of cool. So, anyway, so hopefully you found that interesting. Again, feel free to go back and look through that again. Or pick out pieces if you need to review anything. But I will get back to you in the next day or so with the next lesson. Remember to check on Google Classrooms. I'm assuming you got this from Google Classrooms. The homework sheets that I normally give you will be posted on this assignment, and so you can either print that out or cut and paste it. And then you can just answer the questions online. Obviously, you can type out your answers now. Normally, I don't like you to type out your answers to homework, but you can do that for the next few weeks. Okay. Anyway, have a great rest of your day, and I will talk to you guys soon.